which you have not seen before in the lab.
So this we haven't.
Huh?
This we haven't seen. The wrapping haven't.
Yeah, but I mean, rest of the things in lab, I know that you have not seen, but otherwise, just in general lab. I mean, see, you have probably gone to your BSc, MSc level lab, but I hope this is very much different than those. So, have you found something interesting here compared to your my calling?
No.
Yeah, okay. So, after seeing yesterday's lab, how many of you think that you should take up your career in experiment? These two hands. Anyone from here? Huh? No one. You don't want to experiment. Why?
Want to do.
Huh? What?
Want to do.
Yeah, so just please, can you raise your hand who want to experiment? Okay, 2 and there 2, 4. Okay, why not you guys? Astrophysics. So something like computers are sitting in front of computer and
So then please just mention a bit from lecture 4, exploring fundamental
yeah,
science.
but unfortunately, I mean, I will just cover one slide or something.
Yeah, but just to give them some idea about the exploration of fundamental.
So, but the thing is, like today nowadays, we are finding that most of the wants a peaceful life so that they can sit in an AC room in front of the computer and do very good codings maybe and publish some papers and etc. I don't know how long you will this kind of. It of course depends person to person. But I just wonder why not experiment? Is it something like a problem in our educational system because you do some kind of your lab experiments are like very boring, to be frankly speaking. It's like you know what would be the result, you know what to do, and most of the time you just copy from your previous years, data and video. Yeah, and everything is known. There is no charm in doing that experiment. You know how the Young's-Waters experiment happened and exactly what would be the result. So is that the reason that you are not getting interested in it? Or there is something else, just you want a better life? So I'm just asking those who are not interested in this. For example, like you. See, like for example, astronomy, astrophysics. I mean, you don't need to do experiment in this lab. I'm not saying that. But even in astronomy, astrophysics, it depends on experiment. Like who will build the detector? Who will, I mean, somebody who have built this, what is it? Sorry. Our next, yeah, that's never NCR is, I'm forgetting. GMRT. So, I mean, somebody is nowadays taking data from GMRT and then analyzing this thing. But at some point, somebody thought that we have to build that. And for our national thing, that's a benchmark that actually brought us in the world level, like, you know, the nuclear physics, nuclear test, and etc. But that is another classic example of the experiment which actually brought India into the global level of astronomy and astrophysics. Similarly, LIGO is coming, there will be many more, etc. So there is one part of thing where data will come from some detector who somebody has made it, and some people will sit in front of computer and analyze this data. So why not building the detector? What is the problem? And otherwise you will see what will happen in India. Will only get data from foreign detectors, like let's say your some telescopes, optical astronomy, etc., etc. And in India, we will only analyze that data. So, but that will not uplift, overall upliftment of the Indian science won't happen there because we will be always dependent on them. You will be always dependent on them for their data and etc.
That's my opinion. That we, I feel building a detector involves more of like engineering and
No,
a lot
that,
of different subjects.
no, it's actually together. It's engineering and physics. It's not engineering. Like, for example, you have seen the lab yesterday. If you ask an engineer to make an iron trap, will they be able to do that? Before even machining this iron trap, we have to do a lot of simulations to find out what would be the exact geometry of the iron trap. An engineer won't do that, tell you that thing. Engineer may help you to say, okay, this is how the iron trap can be mounted in a better way. Yeah, but they won't tell you what would be the shape of these electrodes, what would be separations, etc., etc. So that's not at all engineering problem. See, who built this detector in GMRT? Do you know the name? Huh?
They don't know.
So was he an engineer? He was not an engineer. So who built the detector in Hanle optical telescope? Was he an engineer? No. So tell me any physics science experiment in India or anywhere abroad which is built by an engineer. Engineer helps to do some part of it. Of course, they are very helpful, no doubt. But the concept comes from a physicist. If you don't understand what you have to do, you don't know what to do. So it's not an engineering problem at all, it's a science problem. And the science, it's not only physics, it could be mechanical, it could be electronics, it could be anything else, data science, all these things. Everything has to come together and they have to work cohesively together to build something useful. It's not a single person's job to build a very complicated experiment. Okay, anyhow, that's not what I wanted to tell today. So in last three lectures, I was discussing about the basics of clocks. Then I talked about the microwave clocks, room temperature microwave clocks, as well as the cold atom-based fountain clocks. Then yesterday I was mostly speaking about the optical clocks and the difference in accuracy between microwave and optical clocks is about something like 4 orders of magnitude, etc. So today what I will do, I will tell you who cares about this kind of clocks, this kind of so much highly accurate thing. Actually, the next lecture which I will not be able to cover. So there are actually technologies which requires high precision clocks, as well as there are fundamental science to test those kind of things that also requires high precision clocks. Yeah, for example, the last part, which is the application of high precision clocks for fundamental science, that unfortunately I won't be able to cover. I will just mention, well, maybe I will give it one example, but not more than one. But still, I will try to do that. And also maybe one or two examples for the technologies which requires high precision clocks. And one of these classic example is the combination. Yeah. Okay, so let me just go forward. Do you know what it is, this picture? Giravali Observatory, which belongs to IUCAA. You have not been taken to Giravali Observatory, right? Okay, that's pity. You guys should have gone there. It's something like 40 kilometers from here. It's on top of a hill. So that's IUCAA's observatory, Giravali. Very nice place, actually. Should go there. So the last part of Giravali Observatory is something like a very nice 360-degree down, and then it reaches here. This has some height, at some height. So let's say you are here, and you have been asked to measure the height between difference between A and B. Okay, so let's say you are here, and one of your friends is standing there, and you have a task to measure the height difference between you and your friend who are sitting in A and B. What would you do? Very simple, right? You know this kind of leveling machines are available. Yeah, you have seen it on the roadsides. Okay. So you will do a little bit of geometry, like maybe you will take a pointer, you will point towards your frame, then you will make it straight with this leveling machine, you will measure this angle theta, and then if you know the distance, this d, then you can find out the height. Simple trigonometry. Okay. No, there was one more thing. Something is missing. Okay. Some picture is missing. But now let's say the thing is the task is a little bit more difficult, that you have been asked to measure height of the Mount Everest. Now height of the Mount Everest was measured a long time back in before independence. So what would you do? Of course, you won't ask your plane to climb on top of the Mount Everest and do the same thing. That's not a feasible thing. Okay. So how the height of the Mount Everest was measured? Do you know who measured it first? Anybody? Huh? Yeah, Radhanath Sikdar. He was a very young uh, physics mathematician. So he was a very young mathematician from Bengal, and he was working under the British government. And some British government gave him the task to measure the height of the Mount Everest. And the government knew that he will not be able to do that. But after some time, he came back with an answer. So what he did, he measured, he probably, like, this is, let's say, the Mount Everest. Okay, he was standing here, he was pointing some sort of thing towards the top of the mountain, was measuring the angle A, then he moved certain distance D, he was measuring again the angle from that distance, and just use simple trigonometry. I'm not going into mathematical thing, just simple trigonometry. If you know A, B, and how much distance you move, you can practically come up with the height. And he measured it very accurately, very, very accurately with this very simple thing. Okay, so far so good. So you see this. So this during the same time, it was 1954. It was after independence. Sorry. So Radhanath Sikdar measured the height 8848 meter of the Mount Everest, and at the same time, China also did a survey from Chinese side to measure the height of the Mount Everest, and they came up with a height something like 5 meter, 4 meter difference compared to what Radhanath Sikdar was measured. And it's okay, fine. I mean, both of the people were happy. But then recently, just few years back, there was a joint venture by Nepal and Chinese government to measure the height of the Mount Everest again. It's just very recent. I forgot the year, but it's just 2-3 years back. And this joint venture measured the height again, and you see the accuracy is 8848.86 meter. So exactly like this, with the 2 decimal points after the point. So you see, like our Indian mathematicians did a very, very good job with a very basic instrument at that time. Okay, so far so good. Now let's say you have given another task. You know the height of the Mount Everest is not constant, it's still increasing. Why it is increasing? Huh? The tectonic plates is one is going still down, so that the height is little bit increasing. And the increase of the height, rate of increase of the height is actually pretty small. It's something like sub-millimeter or maybe millimeter per year. It's not something like increasing several meters per year. It's very small. So how do you measure the rate of increase of height, which is sub-millimeter or millimeter? Okay, so you can understand, like with this simple technique, you can measure the height of the Mount Everest very accurately. But now, how can you measure this rate of increase of the height? Any idea? I mean, how long? I mean, see, your accuracy is something like that. Over 10 years, many things have happened. It's not feasible thing like to measure something over 10. Okay, I mean, if you don't have very good techniques, that's probably a pedestrian's way. What you said, I agree. But not a real accurate measurement technique. But you can do these things with the help of clocks. We just put 2 clocks, accurate clocks, one on top of mountain, which is possible. And one clock at the bottom, some reference clock. And the tick rates of the clock will be different. Why it would be different? Gravitational density. right? So due to the influence of the gravitational redshift, two clocks at two different heights will have a different tick rate. And by very careful comparison of change of these tick rates, one can find out this submillimeter or millimeter level increase per year. You don't need to wait for 10 years or 20 years. Okay. So I will come to the detail on that part. So, but I just wanted to tell you in the very beginning, in a very simpler words, what could be a very like classic use of a simple, of a clock. But there are much more complex use of it. Okay, so some technological applications of clocks are like accurate targeting. Yeah, if you want to target something very accurately, and this targeting not necessarily has to be like fighter jets or something. You don't need to fight always for accurate targeting. For example, if you want to send a vehicle to Mars or Moon, you know where you have to land very accurately. You cannot land something like 1 kilometer away. So you need to know that position very accurately, and position and time they are just connected with each other. CS square plus B square is equal to C square. Time, yeah. Okay. Times T square. Okay. So you need to know if you need to know the position very accurately, you need to know the time very accurately. How accurately you need to know? If your time inaccuracy is 1 second, what would be your position inaccuracy? Let's see time 1 second, which is 3 times 10 to the power 8 meter. Okay, so just 1 second inaccuracy, you will be just in a different planet. Okay, so that sort of accuracy is required to find out, locate a position. For example, if you want to know something with 10 meters accuracy, roughly speaking, then you need to synchronize time with 3 nanosecond accuracy. 3 nanosecond, 3 times 10 to the power minus 9 second. And 10 meter is even very big thing in today's world. So now I hope you understand why the very accurate time synchronization is very needed for even for our daily life. To all of you, I am sure you use Google Maps. Okay, so that requires this kind of accuracy. I'll come to that exactly how it happens. And then all sort of things like using navigations. You are having very high speed communications. In today's 5G, it's like I think 100 gigabytes per second on that scale. And in 6G communication, which will be in next few years, that will have 100 terabyte per second. Aim is 100 terabyte per second. That's why you are able to download or upload a movie within few seconds, which is something like very large files, or transfer data, very large data from one place to the other place very fast. And this high-speed communication needs very accurate time synchronization, else it will not work. And similarly, all of these things, there are many, many more examples. Okay, so let me start with the very basic things which all of us use. I am sure that you have used the Google Maps. So let's say, this picture is some maps from Delhi. So let's say you went to Delhi to visit something, and then you are sort of lost where to go. And then what you do, you just take your mobile phone out, you start some map applications, let's say Google Map, and it will automatically tell you where you are. Okay, do you know how it works? Anyone knows how it works other than me? Okay, so let me try. Okay, so let me try to explain how it works. Okay, so let's say you are somewhere here. So what happens? You have this device which has some receivers to receive GPS signals, and it doesn't detect the GPS signals directly, but there are a lot of antennas from different service providers on top of the buildings and etc. When you are walking through the road, you will see there are a lot of these antennas which are basically transmitting the telephone signals from different service providers like the Vodafone, BSNL, whatever. So your device basically detects signals from the nearest transmitters. Okay, so the transmitter gives a signal packet, and when it just gives it out from it, it gives a timestamp that I am at time t1, I am sending the signal packet out. And when your mobile device receives that signal, first thing it does, it gives a timestamp that at time t2, I am receiving one signal packet. So this signal packet carries two times other than many other things. One is the time when it started from the transmitter, and second is time when it reaches to the receiver. Okay. So now, if you this let's say t1 with the time difference from these two time steps, one can find this. Your mobile device can find what was the time that this packet was traveling. Then multiplying with c, it can get a distance d, right? So far clear? Okay. So then your receiver will say, okay, I have received a signal packet from a distance d1. But this d1, it cannot say the location because this d1 is just could be anything on a circle, could be any point on the circle, right? So the receiver, your mobile device cannot decide where he is. He can only say, I am at a distance d1 from that X transmitter. So that's why you need to have just one receiver doesn't work. You need to have, okay, this is fine, some numbers. Your mobile device has to receive signals from multiple receivers. The second receiver, it does the same thing, then it will calculate another distance d2, and these two circles can meet only at 2 points, right? Two circles can meet only at 2 points. Then your mobile can say, okay, I am either at this position or at that position. Still, it's not clear. So it needs at least another transmitter to detect another circle. Then 3 circles can meet only at a single point. Basic geometry. Okay. So then your mobile device can say, okay, I am at this position because I have detected my position from these 3 transmitters. But it's actually you see, this is in a 2-dimensional space. I explained. But everything is actually in 3 dimensions. So 3 is not enough, you need 4 because it's not a sphere, it's a spheroid. Okay, just for simplicity, I explained it in a 2-dimensional picture. So you need your mobile device always have to connect to 4 transmitters at least, basically to make it function. And sometimes you see, okay, mobile ka tower nahi aa raha hai, signal mein nahi aa raha. What does that mean? It means it is not able to connect to 4 transmitters at the same time. It may be connecting to 2, 3 or 1, but not 4. That's why it doesn't work. That's what it means. Okay. Okay, so far so good. But see, the life will not be that simple because what you require to work this entire mechanism. So all these clocks, which is at the transmitters and at the receivers, they have to be synchronized. If they are not synchronized, then this won't work. If the synchronization accuracy is 1 second, that means you will find your position with an accuracy of 3 times 10 to the power 8 meters, which you don't want. Okay, so all these clocks which are connected to these communication things have to be synchronized very well so that it can detect its position. And what I told you for about 10 meter accuracy, it has to be synchronized with 3 nanoseconds accuracy. Okay. Now, sometimes you will see, I hope you have experience with Google Maps and etc. or any mapping things. How accurately do you find your position? Just sort of an idea, I hope you have used it. You have used it, right? How accurately do you find any positions, let's say some cafe or some friend's house, etc.? Is it with meter accuracy? Yeah, so something sort of 100 meter accuracy, roughly. That means 30 nanosecond is sort of what we are talking about. And GPS clocks have an accuracy on the order of same thing, in 20 nanosecond to 30 nanosecond, depends on different situations and countries and all those things. So that's the right answer. So that's why we are not able to find anything which is within more or less, let's say 100 meter or maybe 50 meters. meters, something on that order of magnitude. Now, how many of you have traveled in aeroplanes? Okay, I think majority of you nowadays. Okay, that's what basically I just told you. Like these clocks are not identical, so they have some sort of inaccuracy in the synchronization, and that's what decides. It's not a single point, but over some spatial distribution, which is something like 100 nanoseconds, you say, and that corresponds to something like 30 nanoseconds, 500 meter spatial accuracy, but that corresponds to 30 nanoseconds. Okay, so I was taking the example of these flights. So do you know that during the takeoff or landing, most of the flights are human controlled. But when it is in flight, it's mostly autopilot mode. Why that is the case? Do you know that during the autopilot mode, like when you are on sky, let's say 40,000 meter above 40,000 feet above land, then most of the time actually it's in autopilot mode. While pilot doesn't do anything other than just looking everything working fine. But during landing and takeoff, it is autopilot. Human control mode until today. Why that is the case? Just use your general knowledge.
Because during takeoff and landing, that accuracy.
Yeah, why? So what is the typical width of a runway? 30 meter, 25 to 30 meter. So if your timing accuracy is let's say 30 nanoseconds, you cannot detect your position better than 100 meter. So you cannot rely on GPS time synchronizations while landing and taking off. So really pilot have to see where he is landing guided by all these lights and etc. So that's exactly the reason why during the landing and takeoff, it's not in the autopilot mode. And do you know that most of the flight accident happens during the takeoff and landing. Nothing happens most likely. I mean, maybe one or two exceptional cases during the flight. Other than we got some fire or something. But most of the time accident happens because during the landing and takeoff on the runway. There are very nice series like in YouTube or something. Let's see. So, and most of the time this accident happens which are human made. Due to some human errors, this happens. So if you want to get rid of this human controlled mode, you practically have to have much better timing accuracies. If you can bring this 30 nanoseconds to 1 nanosecond, you are done. You don't need to rely on pilot. Everything can be autopilot. But that is sort of a technology that, we have clock. We have clock, let's say optical clock, you have seen it's much accurate than 1 nanosecond. But how to disseminate this kind of time from which let's say we are building in IUCAA, from there to all the airports in India. That's a challenging thing. Okay, to disseminate this kind of accurate times to everyone in the world. But in next few years it will be like that, maybe 10 years or something. And then things will be much different. Everything can be, and this is just one example. Many things need not to be necessarily in human control thing. And machines does actually very few mistakes. Almost none. Okay. So now we understood that accurate time synchronization, time stamping, and time dissemination is a very important factor because of some object examples I told you, but not all. Now I hope you know that the entire world is divided into several time zones. In India, we have only single time zone, but there are many countries which have multiple time zones. For example, US I think have 12 time zones or something like that. Canada has 2 time zones, and etc. But all these time zones, times are divided in terms of a solar day, right? When our sun rises and when the sun sets. According to that, in different countries, these are divided into time zones. Why that is the case? Why it is not just a single time in the entire world that we are following? Because of our biological clocks. Yeah, so we have a biological clock in every living being, and that works according to when it sees the sunlight. So that's why for just simplicity to make everything user friendly, it's divided into the time zones. Okay. But then all these time zones has to be synchronized with extreme good accuracy, not 1 second accuracy, extremely good accuracy. There is a definition of 1 second in an international definition, it's called SI second, and there is an international maintenance of the time at 0 degree this thing, longitude, and corresponding to that, every other longitudes have a time difference. Like every 15 degree corresponds to 1 hour. For example, in India, this is 5.5 hours away from the yeah, that thing. 5.5 hours plus 5.5 hours. So how do you do that thing? Like how do you maintain the national time of each country as per the global standard? So for that, there is an international agency in France. It's called BIPM. This is actually just located in France, but controlled by several different countries, and India is also part of that. So there are every country they maintains their own time standard. In India, National Physical Laboratory in Delhi, they are officially maintaining the time of our country, and similarly for other places like NIST in USA, PTV in Germany, and so on, so on. They are connected to BIPM. They all give their clock's output to BIPM, and BIPM maintains the international time, and then they say, okay, your clock is 1 second inaccurate, your clock is 10 nanosecond inaccurate, please that, and accordingly every country corrects for that. Okay, and that's how these countries are maintaining local time as per the international standards. Okay, so for that, practically all countries nowadays maintain time with atomic clocks. Okay, it could be, I mean, definition is cesium clocks, so it's either fountain or commercial clocks, etc. But finally, you have to even correct this atomic clock based time as per the solar day, because finally we want to wake up at 6 o'clock in the morning, we want to take our lunch at 1 p.m. and so on, so on. So everything, our biological things are connected to solar day. So, and that has also practical reasons why it has to be. I mean, if you are on Earth, then it has to be on based on Earth. I mean, it has to be connected. Your atomic clock time has to be connected to your Earth's rotation time. Okay, for all the practical purposes. So what happens? There is an agency called International Earth Rotation Society who characterizes rotation of Earth or a solar time, solar day, very, very accurately, and for that they use the help of astronomical observation. What do? They look into the very distant object, which is quasar. You know quasar? You guys, quasar you have heard, these are like very distant objects. And so the electromagnetic wave coming from wherever can consider it's a plane wave coming, which is like billions of light years away. And then there are several radio antennas on Earth which are further apart. From, for example, GMRT, there is one in Arizona, there is one in Chile, so far in South Africa, and so on. And these radio antennas, they are connected. It's called VLBI. Anybody knows? VLBI, very large baseline array. So this GMRT is connected to some other radio antennas which are in a different continent, and this is called very large baseline array. So when this electromagnetic wave from a quasar comes, let's say you can find out position of these two antennas very, very accurate with the help of GPS. Very accurate with sub-millimeter accuracy or something. Okay. Now this waveform will come, the plane wave comes, and then they will reach to this antenna and that antenna at a different time because they are in different locations. From the geometry you can see, like it will first reach here, and after a certain time it will, let's say, see it will reach to there, and from the simple geometry, you can find out, okay, what is this angle between these two things. Okay. Now let's say your Earth's rotation frequency or the axis, is it a constant thing? We know 23.5 degrees is the axis of the Earth, and the rotation is like something like 24 hours or blah 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 second. Is it a constant quantity? It's not. This 23.5 degrees actually slightly changes. It becomes smaller and becomes also higher than 23.5. It's not exact this value always. And why that happens? Because of the mass redistribution on an Earth. Let's say there is a volcanic eruption, some lots of masses are coming out and going into some other places. So due to this mass redistribution, it's a huge mass, right? Due to this mass redistribution, this axis little bit changes always. It could be volcanic eruption, it could be glacier coming out, and all these kind of things which could distribute lots of masses. So if there is a slight bit change of the Earth's axis, it can be detected by receiving of the signals in this kind of very large baseline array, because due to slight rotation, this angle, these two angles will be slightly changing. So that means this quasar signal will reach to this kind of radio frequency antenna at a slightly different time. And by doing that, very accurately, it's detected that how the Earth rotation is changing over year or years. Okay? And that is used as an input to the atomic clock constellation. Atomic clock doesn't depend on Earth rotation or anything. It's an independent thing. But atomic clock just maintains time, whatever, as an independent thing, irrespective of rotation of Earth or changing speed of Earth or anything like that. But this is used as an input to give a correction factor. Atomic clock's data is given an input to the correction factor, and that's why you see sometimes there is a 1 second plus or minus in the year. It is called leap second, leap year. You have heard of the leap year, right? What happened in the leap year? Like, due to this change of speed of Earth or axis change, there is a slight bit change in every year. After summing up over some years, when it becomes plus or minus 1 second, not for half second, not for a millisecond or something. After adding up for quite a few years, when it becomes 1 second inaccuracy, it's been corrected in the atomic clock thing. And that is called leap year. That year is called leap year. I think 2016 was the last leap year. Yeah. So this quantity, which is based on the rotation of Earth, this time is called universal time, UT1. This time, which is on atomic clock, based on purely on atomic clock, without getting the correction factor from Earth rotation, this is called TAI, International Atomic Time. TI is in French actually, that's why, but it's called International Atomic Time in English. And when you give correction factor to this one from the Earth rotation, then it is called UTC, Universal Coordinated Time. Did you know about UTC before? Okay. So Universal Coordinated Time is corrected, is an atomic time, but it is corrected from the rotation of Earth and etc. It's synchronized to the rotation of Earth. Let's put it in this way. Okay. And Indian standard time is 5.5 hours plus to the universal coordinate time. By the way, this universal coordinate time will be 0 degree. Okay. And when you go 15 degree on Earth from the 0 degree, then it's plus 1 hour. Yeah. Yeah, but as the Earth rotates, your looking into the quasar will be different. You are not looking at the quasar from the every point. You can connect it to the Earth thing. But you are right. I mean, actually, the detection is on that. Then you find out what is the Earth rotation. Okay. Yeah. So this is practically some things how a nation keeps its time. So for example, this is a picture from CSI and it has lots of cesium clocks and hydrogen lasers and so on, so on. It's connected to, this is a satellite link. I mean, how do you transfer your time accurately to the IPF? You have to use satellites. yeah, you send it through the satellite, and that's the thing which does this. So the data from these clocks are given to the GPS transmitters, and then through the antenna it goes to the BIPM, and also the corrections, whatever it is required, comes through the same path. And then finally the accurate Indian Standard Time is generated, and that is disseminated by several different ways through internet. Depends on what kind of accuracy you require. This is generated and given to common people, to ISRO, DRDO, so on, so on. Okay, that's how the Indian Standard Time is generated, and that's how everything is corrected as part of the international standard, and every country does the same. Okay, now coming back to like this example where I started, like if there is a 1 millimeter change or sub-millimeter change in Everest height, how do you measure that with the help of clock? So let's see how clock can help there. So you see, this is some like a very little point on Earth, and if you look the different surface structure of that small space, there are many different surface structure. What you can see, one is this is the average diameter. This yellow one is average diameter, considering Earth is a this sphere thing. Okay, the average diameter. Then this green one is actual surface. Like somewhere you have sea, so the actual surface is at much lower, and somewhere it's a mountain, so the actual surface is much higher. Okay, so green one is saying the actual surface. The blue one is the sea level. Yeah, the sea level is also different at different points. And what is this magenta one? That is equipotential surface due to Newtonian potential of the Earth. This is called, what is it called? This is called geopotential. And that's also different in different places. That depends on density at that place, at that particular place. The geopotential depends on density. For example, like let's say here you have a big mountain, but the geopotential is not as high as the mountains. Why that is the case? Because you have something probably low density stuff there, some hydrocarbon, something, some gas maybe is there. That's why even if there is a surface is much higher, the density is not that high. That's why geopotential surface is lower. And similarly like that. So this is called geopotential. This is the equipotential surface. Okay. Okay. So now if a clock is at different height from the Earth, due to change of Newtonian potential, the tick rates of the clock changes, which is like this. You have question. This is something like the gravitational rate system. And how it changes? Let's say the Newtonian change of Newtonian potential due to change of height h is can be written like that, where g is the gravitational constant, m is the total mass of Earth, re is the average radius, that is yellow thing, and h is change of height from surface of the Earth to somewhere else. So you can do a little bit math, and approximately this delta u becomes g times me divided by r square times h. And if you put the numbers, you know all of these numbers, then it sort of comes to here, where h is in centimeter unit. H is divided by 1 centimeter, so h is also in centimeter unit. Then the total unit of this quantity is meter square per second. Anyhow, so the change of geopotential, the quantity what we are interested, we found out this change of geopotential due to change of height from the Earth's surface, which is this one. Now, how that affects to the clock tick rates or clock's accuracy? So the maximum accuracy of the clock is delta by f0, and this f0 is changing. Let's say you have two clocks which has this exact same accuracy, or you know what is the accuracy, but this f0, the oscillating tick rates, is changing for these two clocks which are at different heights, and that can be written as delta u by square, and delta u comes from here. If you put all these numbers, then after doing little math, it becomes 10 to the power minus 18 times h by 1 centimeter. That means at an h height, if h is 1 centimeter, then this clock rate will change 10 to the power minus 18. The differential clock rate will be 10 to the power minus 18. So you have a clock here, you have a clock 1 centimeter above, two clocks will have a differential tick rate of 10 to the power minus 18. Okay. So, you know, the cesium clocks has an accuracy of sort of 10 to the power minus 16, best sort of cesium clocks, 2 times the just between friends, let's say 10 to the power minus 16. So that means using cesium clocks, you can resolve a height difference of 100 centimeters. And if they found at present the optical clock has reached an accuracy of 10 to the power minus 20. Let's say it's 10 to the power minus 18. If it is 10 to the power minus 18, then you can actually reach to 1 centimeter level resolution by using the tick rates, by measuring the differential tick rates of these two clocks. So just about an year, more than little bit more than a year now back. So the reported breaks clock accuracy is something 10 to the power minus 21, 7.6, let's say 10 to the power minus 20 between frames. And that has resolved 1 millimeter separation. That corresponds to resolution of height of 1 millimeter or even sub-millimeter actually. So that means if you can make this kind of clocks very compact and etc., which can be transported to on top of the mountain, let's say with some drones or something, and you have a clock, reference clock on the bottom, then you are done. You can measure the differential tick rates between the two clocks over some time and you can find it out. And this is not too far. So this is the picture of Mount Everest. And you see this is the present size of compact optical clock. It's not very big. It's just one 19-inch rack mount. Have you seen 19-inch the server racks? So everything comes in one of the server racks. It will be much smaller in coming years or days. Okay, even this is also possible to probably on top of the mountain if there is a power supply. So this is like, see, I'm not saying that that has to be taken there now, but I'm sort of sensitizing yourself that why these type of clocks are very important even for, this is not fundamental science. Okay, maybe there is some geoscience and etc. But even for normal sophisticated technological things or to find out something very accurately, clock is a very good sensor to do that compared to anything else almost. Okay. Okay, let me skip that part. So, you remember I was showing a plot of 700 years and this axis like how long clock can run to get 1 second in accuracy and so on, so on. You have a question? You want to raise your hand? Yeah.
I'm kind of confused how we can send a signal from the top of the mountain to down and the time taken for it. How can we just accurately measure it?
So that's what I was saying. That even this is like the Mount Everest is only 8 kilometers. We can send the time signals to France, which is let's say I don't know 7,000, 8,000 kilometer away, using the satellites. With the satellite link, like how did you get your television pictures? Yeah, it's through the satellite link. Send the time to the satellite. Satellite will reflect back to the other end, and this is the satellite link. There is another better technology which is called fiber phase stabilizations, which we have worked in the lab, but let's say by this technique using satellites. Okay, so if I look into the last 100 years, the 100 years, let's see, 100 years is not too long, too long back, right? It's something like maybe 2 generations or 1.5. So 100 years back, we have the sort of free mechanical pendulum clocks. I forgot the name of this person. It was basically developed for the marine application. Probably you remember the name of the person? And not Henry, something. I'm forgetting the name of the person. He actually invented that clock, that kind of very good mechanical clock, and he was awarded a prize from then UK government, British government. He is from UK. How can I forget this name of that person? He was a carpenter, by the way. So for marine applications, see, at that time, there was a lot of colonizations were going on. So all these European people were going to different countries, including India and all these places. So one of their problem was the ships were getting lost because they did not know which direction has to go and etc. They only know okay, I have to go to east or north or something. So then the UK government was announcing one thing like if somebody can make a device which can accurately find out position of a seat very accurately, then he will be awarded big money at that time, very big money. And then this carpenter invented that clock, this kind of pendulum clocks, and this is actually still nowadays used as a marine clock. Okay, I'm just forgetting the name of that person.
I don't know. He's saying,
yeah, what is the name?
It's Christian Huygens.
Huygens, yeah, sorry. Right. So like over 100 years, you see that from where we have gone from this mechanical clocks to until today, this is an optical clock. Several orders of magnitude higher in accuracy. And in 100 years, what has happened? I mean, many important discoveries have happened in this last 100 years. Yeah, including quantum mechanics. Quantum mechanics is also 120 years old. It was first conceptualized in 120 years back just. And today we are actually using quantum mechanics for devices. Yeah, quantum communications, quantum computers, so on, so on, so on. So, and all these like developed technologies actually rely on very accurate clocks. So there is a real need of very accurate time synchronizations and stamping, or very accurate, let's say, frequency detections and etc. And that's why there are a lot of attentions to improve the accuracy of the clock, even other than fundamental science aspect, which I have not spoken until so far. Okay, so the best microwave clock is 10 to the power minus 16, and which are more or less good enough for most of the technologies, except the quantum technologies until now. The communication works quite a bit. Okay, you can improve the dissemination's accuracy. You can go from human-controlled piloting mode to autopilot mode to that fine, but still, it's just dissemination technology. Your clock is actually quite good. Okay. But then there is another thing which is exploring fundamental science. And there, this 10 to the power minus 16 clock is not good enough. It is not able to explore or sense any fundamental science thing related to fundamental science things using 10 to the power minus 16 accuracy clocks. And there, we need even better clock, and that's the reason why people are going from microwave to optical clock or even nuclear clock or blah, 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 etc. Okay, so their present accuracy is something 10 to the power minus 21 or 10 to the power minus 20, and even we need better clocks to explore those. So these are obviously the optical clocks, or better than optical clocks, or optical clocks in different elements like nucleus and etc. etc. So the applications is of course better timekeeping, and the present definition of SI time, which is based on cesium, will be changed to a based on optical transitions in few years. It's supposed to change in 2026, but maybe it will be in 2032 or something like that. In every 4 years, there is an agency in BIPN who all these countries sits together, and then they decide okay whether it will change or not. Maybe you know that definition of mass was based on an artifact. First day I started this thing, right? Was based on an artifact of 1 kilogram, but now it's based on watt balance. Okay, this was happening in 2018 or something like that, just few years back. Okay, then there are many technological applications, even normal technologies, common man's use of technology. They use very high precision clocks and etc. And I described one navigation. Then this clock is actually a sensor which senses very small things. Even it can sense dark matter, it can sense gravitational waves, it can sense cosmic microwave background, almost everything. Only thing is, it has to be accurate enough. Okay. So testing basically fundamental science or testing standard model, the clocks plays a very important role, and that's the reason betterment of the clock is an ongoing process almost all the time. Okay. So I would take you like some example quickly. What are these fundamental science possibilities are? One is the temporal constancy of the fundamental constants. Do you know fundamental constants? Which fundamental constants? There are many fundamental constants, right? Like, for example, fine structure constant, or let's say electron to proton mass ratio, or let's say this capital G. Who says that it will be a constant? Who decided? God has not decided that it will be a constant. It's only human beings, for their analytical models, they found if we consider this as a constant, many things we can explain, and which is good. There is nothing wrong in it. So these all constant comes from mathematical modeling. It's not decided by nature. Nature doesn't say, okay, there is a constant velocity speed of light and this is c. We have gone through lots of checks and balances, lots of models, and we found if we consider c as a constant, then many things we can actually explain. But is it really a constant? And we are talking about like a very small change. It's not that every day it is changing by a huge amount of things. Okay. For example, from the beginning of the universe until now, maybe it's not a constant because many things has changed. So one of these things are like few of these things are electron to proton mass ratio is supposedly a constant in our standard model. Fine structure constant alpha. Yeah, supposedly it should be a constant in our standard model, but is it a constant over cosmic time, over age of our universe? Maybe not. So there are theoretical explanations why it should be constant. There are theoretical explanations why it should not be constant. And as an experimentalist, it's our duty to check whether it is a constant or not.
So do we have like any experimental evidence or discrepancies that suggest it is not a constant?
Yeah, very good question. So you know from IUCAA, Sianand, and you know Nisim Kanekar from NCRA. Have you heard his name? These two gentlemen have got Bhatnagar Award because of this searching. So Sriyanand was looking into quasar. Both of them they look into the quasar spectrum. So Sriyanand looks into the UV, ultraviolet, and Nisim looks into the radio frequency because they are UCMRT data. So by looking into this quasar absorption spectrum, which has actually time traveled by millions of years, so it has seen the evolution of the universe, right? So if you detect the quasar absorption spectra very accurately with very high resolutions, it should give an idea whether alpha is varying or not. But so far, they have done fantastic, like really world class. I mean, their papers are getting cited in this particular thing everywhere. By looking into quasar absorption spectra and finding out the variations of fundamental constant, but present day, the detectors, which the data they are using from detectors, the detectors doesn't have enough resolution to accurately say, okay, my alpha is varying this or this much. They can only say my experiment has accuracy of this much, and if alpha is varying, that is smaller than this. Okay, other way around. If my experimental accuracy is this much, and if alpha is varying, that must be smaller than. And the same thing can be done using the atomic clock comparisons, which much more accurately compared to what can be done in the quasar absorption, because atomic clocks are much more accurate compared to the resolution of spectrograph. Those are used in this kind of observational astronomy and etc. So Anand's result or their results are, let's say, here, and atomic clock comparison results here, which is several orders of magnitude below, and still there is no significant finding of variations of alpha. So if alpha is varying, it's much smaller than the atomic clock comparison results. And atomic clock comparison results have reached to what is this one? This one is actually what it says. So see, these are the different experiments which has happened to look for these alpha variations. By looking into the quasar absorption spectra, by looking into the nuclear fission experiment, I am not going into all this because this itself is one complete lecture. Looking into dysprosium data, then optical clock to optical clock comparisons, and etc. And you see all these findings are plotted here, and they are in the same color. For example, this is what these red ones are quasars. This green data is from optical clock comparison. So the actual value mean anything here. The important thing here is the error bars. And you see the base Quasar absorption spectra has this much of error bar. And the base optical clock comparison data has this much error bar, which is nearly invisible here. So optical clock comparison is much accurate compared to any other experiments in these things, but still nobody has found out any variations of fundamental constant. But that doesn't mean that it is not varying or it is varying. That means your experiment is not accurate enough to detect that, and that says, okay, I have to build a better clock. Okay. Yeah. So this is like one thing, like looking into constancy of the fundamental constant is one important fundamental science questions which is explored by very accurate clock. Then similarly, looking into variations of violations of fundamental symmetries. Lorentz symmetry is a fundamental symmetry. What is that? Anyone knows what is Lorentz symmetry? It basically says that any laws of physics or science is independent of the reference frame you choose. Like Newton's law here, it will be exactly same as if you go to a different reference frame. It doesn't depend on orientation of the reference frame, it doesn't depend on speed of the relative speed of the reference frame, etc. That's why it's a law of physics. Third law of Newton's law, first law of Newton's law, it's same wherever you go in the universe. But is it really true? So that also needs to be tested. This is a postulate. Needs to be tested. And that's what says like violations of the Lorentz symmetry, which can be tested using clocks. Third thing is geodetic measurement. For example, this is like geode. This is not Earth surface. This is geopotential surface. That's why it's not at all spherical, but some weird structure. Whether it is varying over time, it is varying over time, right? We know it is varying over time. There are volcanic eruptions, there are breaking of glaciers,
icebergs.
Yeah, all these things. Whichever does some mass redistribution, geopotential changes. Even if there is some nuclear weapon testing somewhere underground, it will redistribute mass and it will change the geopotential. And you cannot take a picture using satellite because something is happening underground. Satellite cannot take a picture. But if you have a mechanism using atomic clocks to really map the geopotential over time, you can say something is happening there because the geopotential has suddenly changed. If it is not volcanic eruption or something natural calamity, then something man-made things are happening there. And that's actually very important strategically. Very, very important. Because everyone does all these kinds of things underground. Okay. And all this can happen, all these are few examples which requires very precise clocks. I don't have enough time, so I'll skip. I thought of giving this Lorentz invariance violations, but let me skip that. So I'll probably come to the end. So this says basically how clock can do it, but that is fine. So now I want to sensitize you, like you know that there is a national quantum mission. Our Prime Minister started this just in April this year, 2-3 months back. Anyone? You don't follow the newspapers? National Quantum Mission. Which was the other one? Big science approval. LIGO, India. Okay, so you all know about LIGO India, but not about quantum mission. So LIGO India approval has happened something like on 6th or 7th of April, and National Quantum Mission was inaugurated on 19th April, just 10 days apart from each other. LIGO India budget is 2,600 crore, and this National Quantum Mission has a budget of 8,000 crore for next 10 years. We are at this moment, the entire world is going through quantum 2.0. It's called quantum 2.0. It's called second quantum revolution. What does that mean? Now we are entering to an era where we will use quantum-based technologies in our daily life to strategic things, etc. What are those? some common examples are quantum communication, quantum computations. You have heard of quantum communication, right? Nowadays, everyone is doing quantum. So this is just two examples that, but quantum technology-based sensors, etc., etc. And there are, other than India, there are 6 countries who have started their quantum missions. They have started few years back, but it's good at least that India also have understood this importance, and India also have started this quantum mission, and we are the 7th country. It's really remarkable that India have understood the importance of that, because the future war will not be based on sending army or nuclear. It will be based on technology. How powerful you are depends on what technological capability you have. So it's very important to have our own indigenized quantum technology in the country, and that's why this mission has started. And this has a very huge budget to start with. And you see, this is I have just taken from Prime Minister's office advertisement, and they have written some of the key things they want to realize, and one is atomic clocks for precise timing. It's not that I have edited. It's Prime Minister's office have understood the importance of these things for strategic reasons, for technological involvement, and etc. etc. And that's why it's a part of this national quantum mission.
It's one out of 4. It's in the right hand corner.
There are many more. These are like more things which is, no, the rest of the things are what it will happen, how many TI. It's from a Twitter thing. So this is the only thing where it is listed what are the things, technological things they want to realize with a lot of importance. Rest of the things are like more.
So I think you have highlighted that.
Yeah, because I am working on atomic clock. Right. And there are of course other things like, for example, gravimeter, communication, navigations, etc. So I highlighted this one because I am working on that part, and that's the topic of this lecture. So now you should think where the future is. Okay, and this future is not for next 2-3 years. This will be the future. We are going from a classical era to a quantum era, so that's our future. For example, just take an example of transistors. When the transistors were invented nearly 70 years back, it was a big size of vacuum tubes and etc. From there, still today it's getting improved. The size of the transistor is becoming smaller and smaller and smaller and smaller, and many like zillions of transistors in a small chips and etc. We are at this moment for the quantum technologies, we are really very in the beginning. Yeah, and it will evolve over hundreds of years or more. We don't know. It will be evolved over a very long time. And at some point, probably you have a quantum laptop on your lap, maybe not you, but your next generation or something like that. It has to evolve to that level. So there is a huge future on these quantum technology related things, and this is not something, of course, we need people who will work in front of computer, but we have to develop this technology in the country. This has, all this quantum technology has strategic importance. So if some other country develops it, they will not sell it to us. Okay, we have to develop it in the country. Exactly the same mistake India was doing for the semiconductor chips. Semiconductor chips are very important, but so far India doesn't produce any chips. We are very good in electronics, but we have to rely on semiconductor chips to China, Korea, so on, so on. And that fault India has realized now, and that's why for this quantum technology, they have started this mission from the very beginning. That we have to develop all the parts of it in the country. Otherwise, we will be only making softwares, like what happens for normal classical computers. We cannot make a computer because we don't have the chip. We can only assemble them. Okay, so I'll stop there. Rethink, reorient yourself. Where is the future, and where to? I mean, if some of you want to take a PhD as your career, think what you want to do. Okay, I will stop here with this comment. If there are any questions, please tell me.
Now, the theories that predict the fine structure constants should change over time. Does it
Yes.
give like accuracy required for a clock to predict that?
Yeah, and you know, theory is a theory, so it always changes. Whenever experiment reaches to the theory levels, then theorists will say, oh, I forgot one factor, I have to add few more loops. That's always the case, and that's actually evolved. For example, the electric dipole moment. Often, okay, we don't know, fine, so let me not take that example. So that's how it happens, because theorists, how do you expect that thing?
She knows electric dipole moment, she knows.
The permanent electric dipole. Well, this is another topic, I don't have that much time, so let's not go into that. So, see, that's an understanding process. Of course, a physicist who is a theorist, let's say, he doesn't know everything. He will say, okay, my theory at this point predicts this much, but then when experiment reaches there and he has no findings, then he starts to rethink. And then he finds, okay, I missed that point. Then I have to add another thing, another few loops and etc. Again, reaches there, and then at some point, you will have this finding. But yes, theory predicts that alpha should vary, and it should have an influence from the dark matter. Now, dark matter also has not yet been detected. That's the next big thing what entire humankind is looking for after black holes, gravitational waves. Dark matter is the real next thing which should be a big discovery. So, if there is a clock which is highly accurate and it may detect dark matter.
And I have one more question. Is Lorentz symmetry related to the equivalence principle?
Yes. Yes, exactly. I did not go into those things. That's also not my topic, sorry. But yes, it is. Yeah. Anything else?
Subhadeep, there's an online question from Sumit.
Yes. Is it in the Zoom chat or how do I see it?
He has sent me, so I can read it for you.
Okay, so let me just read it.
An upper limit on the sensitivity? If yes, then what?
Upper limit of the sensitivity of what?
Quantum clock.
Oh, so the upper limit will be decided by the Heisenberg uncertainty principle, but we are far away from it. So at this moment, we are limited by the technology, like black body radiation and etc. Those decides the present sensitivity, but the real upper limit is decided by Heisenberg uncertainty. Okay.
Thanks.
Oh. Yeah?
No, thanks, I said.
Okay, thank you.
The point is, doing a PhD in this field will not, there will be sufficient funds in the coming 10, 20 years.
Yeah, there will be sufficient, let's just support. And by the way, one thing, so this national quantum mission at this phase, the most important thing that government has said is creating human resource development. Because if you count the number of people we are working in different quantum technologies at this moment, not only clock, in everything, it's only something like 40 to 50 PIs, like project coordinators. I am also one of them. And 50 to 40 project coordinators is a very small number. It's like orders of magnitude smaller compared to what is required. But how do you create these people? Because they have to take it forward to the advanced research. So one of the major mandate of this mission is creating critical mass in the country so that they can do further research to evolve these things. So one of the major mandate of this thing is creating adequate human resource through PhD, postdocs, so on, so on. So what Subhadeep just mentioned, that is very, very important. So that means there is enormous future, enormous scope, and government is really pushing to establish these things. They have learned enough from the semiconductor technology.
And to do astrophysics, one can also detect dark matter.
Yeah, see, all of them are very important. I'm not saying astrophysics is not important. That's also extremely nice things, nice physics, everything is fine.
They've come to IUCAA and they want to do astrophysics.
Okay, so shall I leave? If there are
Recording stopped.